Welcome back, everybody, or welcome, everybody. We are not going to finish on time. I'm not going to keep you here too long, but I do want to give a few irrationality proofs. And especially, I want to end with a theorem about pi. I think that's appropriate, or a couple theorems about pi. Yeah, and the last one I'm going to ask for your help because I cannot think straight at the moment. I did manage to sleep a little bit, but not much. So, but we'll start off with the easy ones. That'll be a good warm up, and then it'll get more challenging here. So we can go to the first slide. I mean, there's nothing on this one anyway, right? Yeah, nice, right? It's my fault.
Classic.
Okay, perfect. Now, luckily, we have a very, very simple definition. This is the only thing we're going to need, really, to prove these, and that is what it means for a number to be rational or to be irrational, right? So a number is rational if it can be written as a fraction of two integers, right? Like 1/3 is a rational number, 5/8 is a rational number. Improper, is that what they're called? Improper ones when the top is bigger than the bottom? Those improper fractions, those are fractions, those are rational numbers. Integers themselves are rational numbers, right? But anything that cannot be written in this form as p over q for two integers is considered irrational. And I had some idea of talking about the quantity of irrational versus rational numbers. Basically, 100% of numbers are irrational, which maybe is a little bit strange, right? Because we definitely know of some rational numbers. But if you were to randomly pick a number from, say, 0 to 1, like you would never get a rational, it would never happen. You'd never get a rational number. It'd always be irrational numbers, right? But we don't, they're like less common in some sense in like daily discourse, right? In fact, for the moment, we don't even know of a single example yet until I'll prove a couple here for you. And I think on the first slide is, we'll prove that the square root of 2 is an irrational number. And so what does it mean to be irrational again? That we will never succeed in writing it as a p over q, where p and q are integers, okay? And so our strategy for this proof and all the proofs I'm going to do is a proof by contradiction. I'm going to pretend it can be written as p over q, and then I'm going to reason to some sort of contradiction that like, oh, that led to the fact that 1 equals 0, which is clearly nonsense, and so the original supposition couldn't possibly have been true. And if you're not rational, that's just another way of saying you're irrational, okay? So let's start off with this one. Maybe I'll give two proofs of it. There's quite a few of these. I think one of these proofs got, an ancient Greek person murdered by his colleagues as well. So they didn't like irrational numbers. And I don't know, maybe it's not like a real thing. It's apocryphal now. But anyway, okay, so how's this going to look like? Well, not Pythagoras, but the person who was tossed overboard that discovered that this was not rational. I don't know his name. What was his name, Anna? Do you know his name?
No, because Pythagoras got murdered for a different reason.
Oh, jeez. They were doing math for 24 hours at a time with no rest, and someone did, yeah. Okay. So let's assume that the square root of 2 is rational. And what does that mean? This is the beauty of these types of proofs here is if I want to prove something is irrational, I have to prove that you can't do something. Like you fail no matter how hard you try to write it as a fraction, you'll never succeed. But if you go by contradiction, then you just assume it's rational and that gives you something to work with. You have a form, you're like, oh, it can be written as 7 over 16 or some fraction like that. And then you have something to work with to manipulate, okay? So if root 2 is rational, that means that there exists integers p and q, say, such that the square root of 2 can be written as p divided by q. Okay? See if I can get maybe a slightly darker one here. Okay. This is okay for everybody, right? This is exactly the opposite of what we're hoping to be true. So I want to work from this to get some contradiction. When you write a number in fractional form, what do you usually suppose about that? Like when you're actually doing homework and you get a fraction, what do you usually do with those fractions?
They're irreducible.
Yeah, you make it irreducible, right? So you make it that p and q have no common factor between the two of them. If p and q have a common factor, divide it out here. So I'm going to add that additional free assumption here that p and q, it actually means they're relatively prime, but I like the term no common factor. Actually, let's use that, okay? So can also assume that p and q have no common factor, okay? And it's actually this that I'm going to end up contradicting. I'm going to show that actually they do have a common factor, but they don't. but they do, but they don't, right? It's a contradiction. It doesn't work. Okay, so with this, we're just going to do some algebra, right? We're totally going to just follow our nose. We have root 2 equals p over q. If you had an equality like this, what would you do with this equality? Okay, yeah, of course, yeah. That's not the first, actually, that's probably the best thing to do, right? There's another thing we're gonna also wanna do for sure. No, I don't know, actually, I thought you were gonna say multiply both sides by the square root of 2, which would have been a really funny thing as well. Did we get it right? Okay, I multiplied both sides by q, great. That's a reasonable thing. We don't like fractions, get rid of the fraction. Now I have this mysterious root 2 times q equals p. Fine, p and q are integers. Now what do I do with this? What's the other thing we don't like? We don't like fractions. We don't like square roots. Square both sides, right? So squaring both sides says 2q squared equals p squared. Now we have this new expression here, okay? There's a lemma we're gonna have to use. I'm not gonna prove it, but what do I know about p squared now? What type of number is it? Even. It's an even number, right? Everybody see it's 2 times something, so p squared is even, okay? And this actually implies that p itself is even. That's not completely instantaneous, but you can go through the examples here of what the outcomes are, maybe proving this by contrapositive or, what's up, Michael? Yes, all right. Hannah already proved this. Yeah, this has been proved. We know that, yeah.
What, 12, 14, 16 hours ago?
A lot more, yeah, a lot of hours ago, yeah. It's not, so certainly the reverse direction is clear, right? If p is even, squaring it, you get an even. That it's square, if you start with an even, that its square root essentially is even, that's maybe not totally obvious, but it is true, okay? Yeah, I want to avoid that intentionally because the next proof I'll use the fundamental theorem of arithmetic and, skirt around this thing. But yes, it also does follow. Yeah, I mean, exactly, right? The prime factorization, no, that's literally the other proof. So, yeah, okay. So if p is even, then this means that p can be written as, say, 2 times s, right? That's what it means to be even, 2 times s. S is also an integer. And now I'm going to substitute this back in to this, okay? So I have 2q squared equals, p is 2s, so I'll just write it as 2s squared, okay? That's just a back substitution there. And then let's simplify as well. Same thing, right? We don't like fractions, we don't like square roots, we don't like unexpanded squares, I guess. I don't know, actually, probably we do like those, but that's 4s squared. So now I have 2q squared equals 4s squared. Another thing we don't like is common terms on both sides that we can divide out by. So divide both sides by 2 to get q squared equals 2s squared. And now, just as above here, what can you tell me about q squared? What? Q squared is even. That's the contradiction, right? I could do it here and have a contradiction, or I'm going to argue here it's even. I like to suspend my disbelief as long as possible and be like, wander along and like, oh, we got it there. But yeah, Hannah's absolutely right here as well. Like q can't possibly be even, right? Because they have a common factor. But here q squared is even, and what does that imply? P squared even implies p even. Q squared even implies q even. And that's maybe our contradiction is now p is even and q is even, so they have a common factor. But I said that they don't have a common factor. Or if you look at it here, this is an even number, this is an even number. It's not in reduced form, right? If they're both even, you can divide out by 2. So this is a contradiction. It's a weird contradiction, I think, a little bit, right? We didn't contradict, I don't know, something earlier here. We contradicted this sort of bonus assumption, but that was okay. If you didn't like this bonus assumption, you can just run this argument by continuously dividing out common 2's to them and then reach the contradiction, okay? All right, let me tell it again with the fundamental theorem of arithmetic that Anna proved, right? So we have that in the toolbox as well. So I'm going to get rid of that and make the same starting assumption there. Oh, I even shouldn't have erased all that, but we can get there. I'll just rewrite this data. So we're going to, again, assume that it's rational. This is the second proof. Root 2 is some p over q. Here I don't even care that it's in reduced form. I don't think it matters here. I'm going to multiply both sides by q, square both sides, get the same expression as before. So this leads to 2q squared equals p squared. There's my expression there. Now, I want to look at the prime factorization of that quantity, the number 2 times q squared, okay? No, actually, let's look at p squared instead. We'll look at both, but that one's easier to look at. P squared is a number. The fundamental theorem of arithmetic says that it has some prime factorization, right? Or maybe it's even better to look at the prime factorization of p itself. I like that better. Let's think about the prime factorization of p itself. How many 2's appear in the prime factorization of p? Some, right? Like maybe not even one, right? Like p could be an odd number. P might even be prime, right? I see you guys are looking ahead too far, right? Like, yes, there is a suspend disbelief, right? P, we don't know yet. But the point is, it has some number of 2's in its prime factorization. But regardless of how many 2's it has in its prime factorization, how many are in the prime factorization of its square? Twice as many as p had, right? So whatever p has, who knows? Its square has an even number of 2's in the prime factorization. That even number could be 0, by the way, but it's 0, 2, 4, 6, 8, and so on. So this number, even number 2's in prime factorization. What about this here? How many 2's in the prime factorization of just q squared? Also an even number, perhaps some other even number. But if this has an even number of 2's in its factorization and I multiply by 2, the resulting number has how many 2's in its prime factorization? An odd number, right? Odd number 2's. But these two numbers are the same. This one has a prime factorization with an even number of 2's. This one has a prime factorization with an odd number of 2's. What's the second part of the fundamental theorem of arithmetic? That numbers all have prime factorizations. Moreover, they're unique, right? You don't have two different ways of factoring. Unique up to like rearranging the terms, right? So you can't have a number with two different prime factorizations. But here I just gave you a number with one prime factorization with an even number of 2's and another with an odd number of 2's. That can't happen. That violates the fundamental theorem of arithmetic. So this is a contradiction, which proves the theorem, right? You couldn't have had a rational here. Okay. So that's the standard starting point here is, do I get 2 QEDs for 2 proofs? 4? 4? A lemma? There were several very small lemmas, but some I stole, so.
My rules, you got like 300.
300.
Yeah. You drew the little box twice. I think you get 2.
Okay, I think I maybe forgot to draw the box the first time, but.
And since they're both contradiction, I think you can also get 2 marks over by the here, there, be drag.
Okay, that's agreed. I'll take that for sure. All right. Well, this is the bad pen. All right, let's go to the next one here. Oh, we're there? Okay, great. So now we're looking at the cube root of 2. And I want to think for a second here. Both the arguments that I just gave can be repeated to make this one work just fine. Right? For instance, you'll either get the wrong number of 2's, maybe mod 3. If you use the fundamental theorem of arithmetic, they won't match up. You'll have more 3's on one factorization than the other, which is impossible. Or you can do a common divisor thing, and maybe you have to take 3 steps instead of 2. I don't remember exactly. And in fact, you can probably imagine that there's an even more general version of this theorem hanging around, right? What if I wrote like this root sign? What do you think other things I can get to be irrational here? Like we saw root 2 works. Just keeping square root, what other things could we do? Yeah, any primes will work here actually. So root of any prime works, and actually this is, if you go through the fundamental theorem of arithmetic argument I just made, 2 wasn't special except for that it was prime. So we could do the same argument with p. You get an even and an odd number of copies of p. How else might we be able to modify this? I think any square-free composite also works. Yeah, definitely. Same idea, right? You just won't have a matching number of things. If it's a square, then we're in trouble because square rooting a square is like just an integer, and so you can also take, I think, any integer root here. I'm not going to generalize quite as far. I'll just write this. But we're only looking at the case for the moment when p is 2 and r is 3. But the 2 examples I gave so far, two proofs I gave so far you could adapt to prove this. But the one I want to give is very specific to this case here, the 2 and 3 case. Okay? So I want to prove that cube root of 2 is irrational. Okay, and how do we prove this? Suppose not. Right? In other words, there exists integers p and q such that the cube root of 2 equals p over q. Good? Same exact setup as before. We could walk through the other 2 proofs. In fact, let's continue to do the same steps as before. Let's multiply both sides by q and then cube both sides. Right, so this implies 2q cubed equals p cubed. We okay with that? That's the result of doing the arithmetic. Okay? And I'm going to rewrite this as okay. Anybody recognize that? This is a false statement. Why is this a false statement? This violates Fermat's last theorem. All right, so we leveraged a nuclear bomb to prove that cube root of 2 is irrational. All right, and notice this only works for 2. Right? If I had a 3 underneath this, then I'd have q cubed plus q cubed plus q cubed equals p cubed. Actually, I don't know if those other Diophantine ones are false or not, but definitely, right? It seems that everyone remembers what Fermat's last theorem is, right? It says that you don't have these integer Pythagorean triples for higher powers here, right? And this is one. This is even a special one where these two would be identical to each other. Those don't exist, right? Yeah, it's very interesting, right? Yeah, exactly. There is maybe a wrinkle here. I cannot claim with certainty that the proof of Fermat's last theorem does not rely on the cube root of 2 being irrational. Like, I don't know the content of that proof. So this may not actually be a proof, right? It might be circular. I suspect this doesn't matter, right? But I don't actually know. It is actually a good warning, right? This is anytime you use a really powerful tool to prove something, you should be wary that that's not being used in the proof. This absolutely can happen. But okay, all right, so that's a huge sledgehammer. Let's do E. I think that's next, right? No, it's okay. Yeah. And I want to show up. I spent so much time with ticks, like trying to do all this cool stuff. Like, look at how cool that is. Also, I wanted like a bunch of, this is kind of interesting. I wanted a bunch of digits of it. So I just like asked Google, like, give me the first 100 digits of E. And like the first answer was clearly AI generated. And I think I copied that, but it's like, that might like just not be accurate, right? It's not hard to generate them and find them accurately, but I don't know. Who knows beyond the first couple. Yeah, the first thing is highly suspicious, right? But you know, that is how it operates. But okay, same idea. How do these start off? How do we prove something is irrational? Yeah. Yeah. What did Molly said? TAC, right? I like that. To a contradiction, we have E equals P over Q. Okay. P and Q are integers here. And we'll need one other wrinkle we didn't use before here. We're going to use that Q is greater than 1. What does it mean if I write it in this fractional form here to say that the denominator is greater than 1 here? It's not an integer itself. I guess we're also getting that it's not negative, but these things we know just from looking at its representation, right? Looking at its representation there, we don't know a priori that it's not rational, right? It might have some insane, far along the way repeating part to it. Okay? So we will use this Q greater than 1 at the end. That was true in the previous theorem as well, we just didn't need it. Okay, so let's recall, this wasn't too long ago. Nana told us a form of E, right? We know E is the limit of 1 plus 1 over n to the n, but Nana resolved using the binomial theorem that E is in fact equal to the infinite sum k from 0 to infinity of 1 over k factorial. Right? We saw that one. No. Sure. Yeah. Once you put it on the board, it's like gone. Yeah, I totally understand. So we're going to use this fact here. We know that it can be written in this form here. Right? Actually, just saying this now, it's kind of funny, right? This statement here almost seems like it says that E is rational, right? What is this sum here? It's a sum of a bunch of fractions, and summing rationals gives you rationals, except for if you do infinitely many of them, like it's a little bit, you're taking a limit, it doesn't follow those rules anymore. Okay, so let's write the following. And let me also rewrite this because it's a little bit helpful. This is also the same as writing 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial. It's just that infinite sum there, right? And this 1 comes from, when we evaluate this at 0, we get 1 over 1, this one here, and then 1 over 1 factorial, and so on. So let's write out the following expression, right? Let's write q factorial, that's this q here, right? We don't know what that is, it's just some integer, times e minus the first q terms of its infinite representation, okay? So it's that's like the partial sum, we call that. So I'm going to subtract from it 1 minus 1 over 1 factorial minus 1 over 2 factorial minus 1 over 3 factorial minus 1 over q factorial. Okay? That's something. I don't know what that is. But actually, you can think of what's in these parentheses here as like this part here is an estimate for E, because that's the truth of E there. And so presumably this difference is getting smaller somehow. That's actually not important, though. And I claim that this is equal to the following expression, and this is incredibly simple here. Q factorial, same Q factorial as over there, times, well, let's think about this. E is that entire sum there. If I subtract from it the first, it's Q plus 1 terms of it, what is left? Yeah, I think, yeah, we'll start from 1 over Q plus 1 factorial, right? That's the next term, right? It's like this is all of them in E, and I said that gets canceled, that gets canceled, that gets canceled, that gets canceled, up until the Q, 1 over Q factorial. So that'd be the next one that was left over, and then plus 1 over Q plus 1, Q plus 2 factorial, plus 1 over Q plus 3 factorial, plus, just goes on. It's an infinite sum inside of this, right? It's just the part, you don't call that a partial sum, right? That's like the tail of the sum here from the Q plus first term and so on. All right, nothing special here. All we did was reconfigure this, and we had the Q factorial times on both sides. Okay? Let's look at the expression on the left here. What happens if I multiply Q factorial through? Yeah, and check this out, right? So this times each of these is an integer, right? Because everybody see that Q factorial contains 1, 2, 3, 4, 5 up to Q. If I divide it by these factorials, they just cancel out some of the early terms, and I'm left with things in the numerator. But look at Q factorial times E. Ordinarily, that's just Q factorial times E. But what regime are we operating in? E is P over Q. So multiplying E by Q factorial actually literally gives me P times Q minus 1 factorial. Right? That's literally what it's simplified. And ordinarily, that's not true, right? But because it's in this form, it does. And so this product, Michael said 99% of it, right? It's an integer, right? This is an integer, and we subtracted off a bunch of integers. So this expression is an integer. Okay. Nice. And we could only leverage that it was an integer because E was rational, right? E is rational, so we could multiply it by something to turn it into. We didn't even need to multiply by Q factorial to do that, by the way. Right? Obviously, E times Q is the integer P, but I wanted to deal with these ones too. Now I want to address this side. That side can be rewritten as Q factorial. I'm going to replace it with an upper bound, okay? So I'm going to replace it with something larger here. Do I want to do that? Maybe I want to multiply. I'm going to multiply through by Q squared first. Okay? So this part here, Q squared, Q factorial. So if I multiply through by q factorial, what happens? Let's look at this one here. What's left here if I multiply through by q factorial? Yeah, just 1 over q plus 1. The q factorial goes on top. All the terms but the very last one on the bottom disappear. So I get a 1 over q plus 1 plus, what's the next one look like? Exactly, yeah, 1 over q plus 1 times q plus 2. Right, those are just the next two terms that didn't cancel with the q factorial. And so on, right? 1 over q plus 1, q plus 2, q plus 3. And this continues on into infinity, right? The denominators keep getting smaller and smaller and smaller. They're collecting up more terms. Now this is, at most, right? For now it was equal. Now I'm going to simplify this here. So this is 1 over q plus 1. Plus, here, instead of dividing by q plus 1 times q plus 2, I'm just going to divide by q plus 1 squared. Right? 1 over q plus 1 squared. Everybody agree that this number here is larger than that number there, so replacing the upper bound is okay, and continue to do that. Right, same thing, just replace that with a q1, that with a q1. You made a bigger number there, and that it goes on forever. What kind of sum is this? It's geometric, right? That's a geometric series, and it has a formula, right? We know the exact value of these. It is, I'll write it like this because this will remind you of the formula. A over 1 minus r. Anybody remember this? R is the common ratio. What's the common ratio? 1 over q plus 1, right? Each term is multiplied by 1 over q plus 1. So 1 over q plus 1. And here I usually mess this up. A is the first term. I prefer my geometric series to start with a 1, and then a is 1, and that's it. But that's not what's happening here. This one starts with 1 over q plus 1 as well. So that goes up here. Yeah, that's okay. Anybody see what we get here? Q plus 1 over q plus 1 minus 1 over q plus 1. So you get q over q plus 1 underneath 1 over q plus 1. It's 1 over q. It's q. Wait, something's wrong. No, Anna, you're right. I'm sorry. Yeah. 1 over q wouldn't have been, or 1 over q is way more interesting. Yeah, we can double check it. I knew it was going to be something really pretty, but yeah, so 1 over q plus 1. Yeah, you have q over q plus 1. Q plus 1 is in the denominator of the denominator. It flips up to the numerator. It cancels with that. Good. I don't want to write out more than that, but you get 1 over q. What can you tell me about 1 over q? It's not an integer, right? So what happened? An integer, whatever, we don't know the integer exactly, is equal to a non-integer, 1 over q. Right? Yeah, you're right. I didn't say equal. Yeah, I have an integer that's at most 1 over q. I finally used that assumption there, right? Just barely. Actually, maybe it's better to add that. That means that sum is less than 1. And that means I have an integer on the left-hand side that is less than 1. I should also specify that it's greater than 0. There are integers, that are less than 1, right? But this one isn't. How easy is that to see, actually? Oh, it's super easy to see, right? What I've subtracted in here is positive, right? It's e minus sum of e, not all of e. So this thing is greater than 0, multiplied by q factorial. Yeah, great. So I should add this. Oh, okay, cool. It's good to find those things. Okay, so now we have an integer bounded between 0 and 1. There's no such integer, okay? So that's a contradiction, and that proves the theorem. You mean here? Oh, have it here as well?
Right, because it would be p, if it was 0, we have p over 0. That seems to be an issue.
You can't do, yeah, but having q itself greater than 1 already frees us from that, right? But that actually is in principle being used here, although I can't get a factorial to be down to 0 anyway. But yeah, it's just simply because this is at least 1, or actually greater than 1. and this is, that's tiny, right? For larger and larger q's, this difference gets smaller and smaller and smaller, but it doesn't vanish until I take the limit. But I explicitly didn't take the limit here, right? I just took some partial amount, depending on this q. Right? Anyway, that one's very mysterious, right? It's like, doesn't reveal much about what's going on, but not the next one won't either. Yeah, more ticks fun. Yeah. So I'm not going to prove this, but this is an amazing conjecture, right? So if you've learned about the harmonic series, and you have, right? It diverges, right? It's always our favorite example. Like, well, wait, the thing inside goes to 0. Like, shouldn't it converge? Like, they're getting smaller and smaller and smaller. And it's a very nice induction proof that we proved in this, not this time, but last year, that thing goes to infinity. And it goes to infinity approximately the same rate that log n does. And actually, what this expression says, it goes approximately the same rate, but not exactly. So this here evaluates how quickly the harmonic series goes to infinity compared to the log n. Log n also goes to infinity. And it's this constant, this Euler constant, of which there's the first, I don't know, however many terms. But that's not known to be rational or irrational, which is sort of remarkable. This is like after pi and e, that's the next one that like is interesting, I think. And the fact that it's open, whether it's rational or not, is pretty amazing. I mean, it's definitely irrational, right? There's like no way. But anyhow. Okay. I feel safe conjecturing that it's irrational, and I wouldn't be sad if someone like disproved my conjecture, but
We'll probably prove it in 50 years.
right.
Fairly convincing.
Fairly convincing, and then we'll sit on it for yeah. Okay, so now the big one, pi is irrational, and this one's the hard one. It's not necessarily much longer, although it is longer than the previous here, but it involves some stuff that I'm going to need the audience's help with in two ways. One, just recalling a few details. Two, just believing what I say and not forcing me to work out the details, right? I don't want to go through the details. They're not hard to check, though. Okay, so, all right. We are going to do the same thing, right, as we always do. Suppose that pi can be written as p over q. All the proofs work this way. Okay, and remember in the previous result, we used the existence of that format there to sort of build up some inequality there that was just patently false. It's a similar idea here. We're going to find, again, actually, we're going to end up finding an integer less than 1 and greater than 0. Same exact idea in that sense. And again, it will also depend on the value of p and q will tell us how to find that integer. In the previous one, actually, p didn't play a role at all, did it? Right? P literally never appeared in the proof. This one, both p and q will be used. Okay. So suppose that, and we need to consider the following integral. Okay, so consider, I got to be careful. Board space is going to be at a premium for this one. Not much higher? Oh, okay, gotcha. Yeah, okay. So consider IN, and this just isn't going to work for me. I got to write this large. Too important not to. So we're going to consider IN, which is q to the 2n over n factorial, integral from 0 to pi of x to the n, pi minus x to the n, sine x dx. Okay? That's the definition of IN, right? There's different I5s, I7s, I12s, I whatever. So it's just relatively standard integral, right? This isn't that wild. I mean, it's not the easiest to deal with, but yeah, we're going to discuss this one at some length. And the first thing I want to do is claim something about the behavior of IN here, okay? So the first thing I'm going to claim is that IN is at least 0, and I'm not going to prove that. Probably it's easy to see, though. Actually, yeah, I didn't think about this at all. Oh, here's what I would do. Well, okay, it's not that easy to plot this because it depends on n, but I am going to use a hypothetical picture, and it's just a bump above. What's that, Michael?
integral was something positive.
Everything's positive, yeah. The picture I can represent this way here. This scaling factor in front doesn't hurt me, right? It might shrink it down, but it's not going to magically turn it negative, right? So let's suppose that the picture looks like that. I don't know, I don't know what it operates like exactly, but Michael's spot on, right? Everything here is positive on this interval here. Great, okay. So that part of the claim is proved. The other part of the claim that I'd like to prove is that In tends to 0 as n tends to infinity, okay? And this turns out to be incredibly easy. So the way that I'm going to do this is the integral on this interval of this function is just the area under this curve, right? That's what the integral is. What I'm going to do is just overestimate here. And this will work well enough for me. So let's look at, for instance, what's the largest that sine x can be on the interval 0 to pi? Yeah, well, it's not getting above 1. Doesn't matter where it is, right? So sine x is at most 1. I could literally drop the sine x, and this integral would only increase in size. How large can x to the n be on that interval? Pi to the n. That's the largest value there that this can be on the interval. So that's max size pi to the n. What's the max that pi minus x to the n can be on the interval? Pi to the n, yeah. Okay, so what that means is that this curve is below, I mean, it might reach it in principle, pi to the 2n, right? 2n. Everybody agree with that? This area there. And so what is the area of the rectangle here that contains the area of the curve there? Pi into the 2n plus 1, right? Everybody see its height? Yeah, maybe my illustration isn't the best here. This is, the height here is pi to the 2n, right? And the width here as well, clearly indicated as pi. And so, oh yeah, we're using Michael's, results about the area of rectangles that we are allowed to multiply base and with
Do that now.
Yeah. So what does this mean? This means that In is bounded above by q to the 2n over n factorial times pi to the 2n plus 1, right? Because I've just replaced the integral with this constant function that's larger than it. Let's rewrite this real quick as q times pi to the 2n over n factorial. Why do it that way? Whatever. Times pi. In the denominator, we have a factorial function. In the numerator, what do we have? Yeah, maybe that's a great idea. Let's move the 2 inside here. So squared to the n. That's a little bit easier to observe. Q times pi squared, what is that? It's just some number, right? I don't know what number it is. It's just some number. In fact, I can even make estimates about it. Like p isn't that. I'm using q. Q isn't probably that. Actually, that's interesting. Q might be enormous, right? We don't really know anything about q. But the point is q is just some number. It's just some number. So I have some number times pi. Oh, actually, yeah, pi times q is just p. So it doesn't matter. What Anna said is exactly right. That's just some constant number. So this here is just a simple exponential function, right? This goes to 0 as the factorial function dominates any exponential function. This is a fun little exercise to have. Is it doesn't matter how large you make the base here, the factorial always wins this fight here. So if you divide the 2 here, n factorial will, you may have to get really large, but it definitely tends to 0, okay? So these INs, these integrals get smaller and smaller and smaller. And why? Well, basically just because this thing just takes everything over and sends it to 0. It doesn't matter what your integral is doing. The q to the 2n doesn't even help. Okay. All right, so we have the 2 parts of the claim there. They're true now. I won't give myself a QED for them. Okay, and I still want to keep this one. There's definitely a lot of pi's. There's like so many pi's in this proof. Yeah, I think I've got like at least 3. Oh, I see more than 3 on the board. Oh my goodness. I'll give 5. There's more coming, so All right. So now, what I want to do here is prove to you that In is an integer for all n. Okay? Do you see what the problem would be? If In is an integer for all n, yet it's at least 0 and tends to 0. Then at some point in n, it's within the interval 0, 1, and it's maybe we want strict there to avoid the same problem as before. That's definitely also true, right? That it's definitely not equal to 0. Okay, same exact idea as before, but in the previous one, we kind of knew where our limiting factor was. It was at q factorial. That was the place to take it where we ran into trouble. Here, I don't know. I just know that it tends to infinity, and it depends on the relationship of the exponential and factorial function, but we don't have to unpack that. We just know that it gets as small as we want. Okay, so how are we going to prove that? We're going to prove it actually by induction, although I'm not really going to do that. But I'm going to show you the idea here. And I'm going to follow the format. You can also, there's a video on YouTube. Anybody know the Mathologer YouTube channel? It's another one like 3 blue, 1 brown, and things like that. Mathologer is completely amazing. And I took this treatment from there because it's just amazing. So you can also check it out there. But I'm taking some of his choices about how to present here as well. Okay. So I'm also going to claim the following. Actually, before we even do that, I'm trying to figure out when I want the punchline to occur. I'll say it in advance, okay? So I claim that in is an integer, okay? How would we go about doing that? Well, why don't we compute a couple of in values until we really get exhausted with it? And this is where you're gonna have to believe me, because I'll just say, you can probably guess, how do you integrate a function like this? What's gonna happen? Actually, in disguise, we won't use that directly, but yeah, what else? Did I hear it whispered? What did you say? Yeah, we're gonna integrate by parts, everybody's favorite, right? And actually, we're gonna have to do it n times, right? Which is horrible, but I'm gonna do a proof by example here. Actually, integrating by parts n times is just induction in disguise, right? You don't have to do n times, you can do 2 times. But I'm gonna do it, we'll get there in a second. So what's I0? This one at least is fine, right? I0 is, we have q to the 0 over 1. So it's the integral from 0 to pi of, hey, this is great, 1 sine x dx. Anybody remember what that one is? Yeah, on the interval 0 to pi though, right? So we remember what the integral of sine is, and then we have to, all you have to do is evaluate the integral at 0 and pi and 0 and subtract them from each other. Anyone care to guess if they don't remember? 0 is a reasonable guess and would be enough for our purposes. It turns out it's not 0, but that's fair. It's 2, yeah. It's one of those 3 basically, right? What's important is it's an integer. You can check this one real quick. It happens to be 2, it's really nice. Okay. All right, let's think about I1 for a second. So I1, you get q squared over 1, just a q squared up front. And then you have the integral from 0 to pi of x, pi minus x, sine x, dx. That's already trouble. You're already definitely have to do integration by parts here. I'll at least ask. I want it to feel like we're really doing something even if we skip some of the integration by parts. If you were going to try integration by parts, what would your u and dv, what would you want to try here? These are pretty standard, right? Any call-outs? Yeah, I'd prefer to integrate that as well, right? So that'll be my dv, this will be my u, and this will be true throughout. I think this is pretty standard when you have these mixed polynomial trig functions. That's usually what you do. Doesn't mean you always do it though, okay? The one nice thing that is worth looking at here though is the following. I'll leave the q squared out front here, and this will come up a few times, is you also have to help me remember what integration by parts does here. I'll evaluate uv, I'm just gonna write it like this, from 0 to pi, right? That's the correct first part. But I don't even care what v is, because look at this beautiful function evaluated on the interval 0 pi. What happens to it? I get 0 both times. When I plug in 0, this is 0. When I plug in pi, that's 0. The whole thing zeroes out. So this computational part just vanishes. That's one advantage of this in integration by parts. That front part always going to disappear, even when I have exponents on them. You see this? What happens when I evaluate this function at 0? 0, or pi? Pi. So that's going to drop out. So that makes our integration by parts much easier. And so then we're left with, actually it's just a single integral. from 0 to pi of here we get duv, right? Okay, so v at least is easy. What's the integral of sine x? And now actually the integral, not the evaluation. Yeah, and I made a trick here. There's actually a negative out front of this part, but the negative cosine is going to cancel with it. So that's the integral of that. It's not the integral, there's a negative, but it cancels with the negative. Remember, integration by parts, it's minus the integral. And then I have to derivate this part here. That's not that bad, right? That's not that bad. We'll do this one here, but then we won't do another. Derivate, right? Something's bothering me. Is it? We're taking the derivative of. And what is this? The product rule? Derivative of that times that plus derivative of that. So what, minus x? Somehow that wasn't what I was expecting, but maybe it doesn't matter.
Multiply it out.
Oh, that's even better. That's even better. Yeah, right. And actually, that's actually what I want. I'm just going to show it because we'd still have to work, but you can turn this into two integrals, right? I'm going to pull the pi out front of one of them here. Okay, see, I already don't want to do this anymore. But the thing is, okay, so what happens, this isn't too implausible. I'll write out what we get, and we can look back at it. I know what's in my head. Yeah, it's this. Okay. So I claim that this is going to end up being 4q squared, the whole thing. That's the q squared. What I'm saying is the integral inside of here is going to be 4. I mean, I can't convince you that it's completely obvious that it's going to be that, but you just go through it. A bunch of terms end up canceling. It's not that bad. I just don't want to do it, and I don't want to do any of the other integrations, to be honest. But what's true about that number and this number? They're both, yeah, and they're both integers is what I care about here, right? And the q squared is, remember, it came from the representation of pi there. Okay, so now for the last claim that will give us this one, is that in itself forms a recurrence relation. And this one I have to just copy. So in equals 2q squared, 2n minus 1, in minus 1, minus p squared, q squared, in minus 2. Okay? That's the claim we make, okay? And that, together with these two, would prove this claim. Does everybody see that? Well, we should check here. How do I compute I3? I plug in 2 for that, and that for that. And look at all the other terms here. Integer, 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 integer. In is an integer, right? It's just a recurrence relation. It also, crucially, right, is initialized by integers. So I3 is an integer, I4 is an integer, I5 is an integer, and so on and so forth. So I'm going to erase these. Those, together with the existence of this recurrence relation, tell me that I is an integer, which would contradict this. So what remains to prove is, does this crazy recurrence hold, right? It better hold here. And I'm going to try and give you a rough idea of why that is. But does everybody see now, if I can establish this relation, the proof is done, right? Because then I just wind it up and get every one of these as an integer, and yet they tend to 0. Okay. And so earlier this morning, I tried to sit down and prove this by hand. And the argument isn't difficult. It's just integration by parts, again. But with the ends and stuff, it's just completely overwhelming. And so what Mathologer does that I liked very much was just established it for n equals 5. This is what my favorite type of proof by example, right? It's not actually a proof. But I will show you that it holds for I equals 5 without doing all the integration. And then I hope you'll believe me that, like, oh, 5 wasn't really of any material substance here. We could have done it with n in the place of that. I just don't, I want to be able to multiply numbers. I don't want n times n minus 1 times n minus 2. I just want 20 or whatever. Like, it's way better. Okay, so what I'm asking here is, oh yeah, and actually, maybe we'll do that after. So I of 5 equals, well, its formula is right there, right? And in fact, let me do this. This is always risky. Nah, I won't do it. Q to the 10 over 5 factorial, right? That's that leading part there. And then I have integral 0 pi x to the 5th pi minus x to the 5th sine x dx. Okay? Here we can integrate by parts just fine, right? We do the same thing as before, which we failed to do correctly. I mean, we gave up. We didn't fail. And this is, yeah, sort. I mean, maybe. So here we went with u and dv, right? And we'll do the same with this. And let's think about for a second what will happen when we do this. And then I'll tell you what it comes out to. So we still have this q to the 10th over 5 factorial up front, which is kind of annoying here. In the evaluation part, we're going to have the same thing as before, right? We're going to have this times the integral of that evaluated at 0 and pi, which just zeroes out. So that part vanishes. And then we're going to have a minus negative cosine x, which will remove this negative again. So we're definitely going to have a cosine x. And then all we have to do is chain rule on this simple thing here, which, I mean, we could sit out and write that out. The harder part is how to split up the integral in a way that's useful for us for the next step, okay? But taking the derivative of x to the 5th pi minus x to the 5th, that's no sweat, right? So let me tell you what this comes out to. Well, we could easily do it by hand. It comes out to the integral from 0 to pi. Oh, yeah, this one we don't have to range terms. 5 pi minus 2x, x to the 4th, pi minus x to the 4th, and then the cosine x dx. Okay? This expression here isn't exactly I4, but it is reminiscent of I4. What happened to the exponents on things? Right? X to the 4th, pi minus x to the 4th. That's what I would anticipate seeing in the I4 term. Of course, there's a cosine here instead of a sine, and there's other stuff that doesn't belong there. Right? But this is the first step. We do integration by parts twice to this, okay? So same question, how would I deal with this expression? We do integration by parts again, right? So integration by parts yet again, and we have q to the 10th over 5 factorial times something. Let's think this through again. If I do integration by parts on this, that's going to be my dv. What happens when I integrate that? I get to sine. Ooh, that's good, right? I want sine to reappear. So I'll put this at the end and then probably erase it and move it again, but sine dx. And then this one here, I'm going to need to take the, okay, yeah, let's don't forget, remember the leading part here where I actually evaluate? Same thing as before. I'm going to be evaluating this product on 0 and pi. It just vanishes. So I only have the integral part, and it's a negative of the integral, right? This time the sign doesn't give me a negative. 0 to pi. And then I just have to chain rule this, and this is where I gave up when I was working with ends, because again, it's totally doable, but there's 3 terms there. It's just like long, and you're guaranteed to make a mistake, and it was no fun. And then you have to break it up, right? So I'll tell you what it comes out to, and in the form that is useful for us. It comes out to, I'm going to split it into 2 integrals here. 20 times 4 plus 10. It's a weird way to write, what's that, 90? And 0 to pi, x to the 4th, pi minus x to the 4th, sine x dx. That's good, right? Minus 20, just 20 pi squared, 0 to pi, x cubed pi minus x cubed sine x dx. That's what this evaluates to. Let's think at least for a second if it's plausible, right? If I apply chain rule to this, I'm going to see, like when I take the derivative of that part, this expression with other stuff around it, but that's going to leave me x to the 4th pi minus x to the fourth here, right? When I derivate, wait, how am I going to get that one? You see what I'm saying? This one's very plausible. That one, when I take the derivative of other terms, like I'll definitely see an x to the third and something to the fourth, and a this to the third and this to the fourth, but I don't see the two combined at the moment. But you know, it's a lot more complicated than that simple thing. It'll work out, I guess, you end up with this thing here, okay? Yeah, anyway, it's not completely obvious. This one I think is at least quite plausible, although it's not instantaneous from there, it's just plausible, right? But what's nice about the expression we see here? Like, what does this look like? It looks a lot like I4, except it's missing what should be in front of I4, right? I4 should have q to the 8 over 4 factorial. But look what we have here. We have q to the 10. So if I multiply that through, I get a q to the 10 times this here. But go back up here. Look what's actually in front of I4. I'm trying to prove this recurrence here. Not find, I know what I4 is. I can write out its expression. Q to the 10th, there's q squared there, right? And then the remaining q to the 8th would be exactly what I want there. Now, do I get a 4 factorial where I want it and 2n minus 1 into 2? Yes, you'll have to believe me, you do the arithmetic, it works out, right? Again, that's like 15 minutes of doing work to get that to work perfectly. What about this thing here? It looks like I3. And when you end up doing these substitutions, let me write out what you get, and then we're at the punchline here. So you end up finding you're going to get I5 equals 2q squared, 2n minus 1, I minus 4, minus, and this is where things are interesting, there's no p anywhere here, right? There's q's over there. There's no p, but there's a pi. Okay? Let me get this right. Yeah, that's also... You get q to the 4th pi squared, I4, right? Should be that's all I3, sorry. Right, that's what I3 anticipates. Right, this thing looks like I3 with the wrong coefficient here. This looks I4 with the wrong coefficient. You multiply through, things work out. But look at this amazing thing here. What do I want that to be? So that the recurrence, I'm trying to prove the recurrence in general. I should see p squared q squared. I instead see q to the 4th pi squared, but what's pi? This is when finally I use this, right? I haven't used it till now. Pi squared is p squared over q squared. That is p squared over q squared, which drops that to q squared and leaves a p squared. It gives me that. The recurrence holds, okay? With a lot of hand waving, but this is just calculus. This is just integration by parts, right? No small matter, but still. That's the end of the proof, right? Now, what's going on? In is an integer and tends to 0 and is greater than 0. That's not possible, right? That's one of the shorter proofs, probably, that pi is irrational. Most of them involve integration by parts, as far as I know. So anyway, okay. Maybe just go to the last slide here, and I'll just leave this one because it's just so freaking hilarious, right? Like, so we have pi to the pi to the pi to the pi, right? Call back, right? And end to the end to the end, and I asked then about 3, right? There was a reason that I asked about 3. Even that number, we don't have any way of computing, actually, easily. If you do, like, just think about 3 for a second, right? The top exponential is 3 to the 3. So you have 3 to the 3 to the 27, right? So you have 3 to the 27. What's 3 to the 27? It's like lots of digits already. That's your exponent, right? So you can't even compute this number, but imagine trying to do it with precision, not with 3, but with pi's. Like, I literally don't know what a computer would do in that. I wouldn't be able to do it, but like, you can't even, like, right? Because if I ask you, is that an integer, what do? Plug in, like, just look at it, right? Like, rationals you don't know, right? Like, if you write out trillion digits of a rational, you're like, maybe it repeats eventually. But I can easily identify a number, whether it's an integer or not. Is there a decimal or not? Here you can't even figure that out, which is just, I think it's amazing. It's such a compact expression there. But Anyway, okay, I think we should stop there. Thanks everyone in the audience, both here and online. Another very successful Pi Day. I had a blast. I really appreciate y'all being here. A few legends, well, all of you are legends, but a few of you were here for like 24 hours, including several, people. Yeah, I mean, that's just amazing. Yeah, 20, I mean, we're close to 25. So the problem is that you can never go back. Every time it has to be bigger and better, and so yeah, be prepared. But just like recruit more people. Yeah. Oh, by the way, right, come on, like there's more pies on the board than are there practically, like this, anyway.